Aloha, Richard Halverson here. This is ICS211, and today this video I'm gonna cover start us out on trees. So let me share my screen. And so I think I'm gonna try to get through 1, 2, and 3 sections 1, 2, and 3 today. Let's start with binary trees. This first section. Let's see, basics. Let's do a presentation view. A binary tree is a node. In a binary tree, a node has up to 2 children, known as the left child and the right child. A leaf is a tree node with no children. An internal node has at least 1 child. A parent is a node with a child, and it is said to be the child's parent. This is all obvious stuff. An ancestor is a node's ancestors include the node's parent and parent's parent and so on up to the tree's root. And then the root is the one tree node with no parent. It's called the top node. So you've seen pictures like this before. This is a tree. This is the root node, and internal nodes got children, and leaf nodes don't have children. This is a list. So click through this to make sure you understand what these are. An edge is a link from a node to a child. So this is an edge right here. This is an edge right here. And the depth, a node's depth is the number of edges on the path from the root to the node. So the depth of this node F is 2 because it's 1, 2 edges from the root. And the height of a tree is the largest depth of any node. So the height of this tree is 2 because this is the farthest away node. This is a depth of 2, this is a depth of 1 because it's just 1 edge, and this is a depth of 0 because it's got no edges going up. Now there are these definitions of full, complete, and perfect. A full tree is a tree that doesn't have any nodes that only have 1 children, that only have 1 child. A full binary tree, every node has either no children or 2 children. Okay, a complete tree is a binary tree that is complete if all levels except possibly the last level. All levels contain nodes. All levels contain all the nodes except for possibly the bottom level. And if the bottom level does not contain all nodes, then all the nodes are to the left. Okay, so after we learn how to represent binary trees in different ways, when we represent a binary tree in an array, in a sequential array, then a complete binary tree fills up all of the elements up till the end, and there's no empty elements within the tree. You'll see what that means. A perfect binary tree is a tree that where all the internal nodes have 2 children and all the leaf nodes are at the same level. So it's going to have 2 to the n minus 1 nodes, where n is the number of levels. All right, so for example, this here is not full. Wait, why is it not full? It's not perfect because it doesn't have, there's no child here, there's no child here, there's no child here. It's complete because it's not full because this F only has 1 child. If F had 2 children, then it would be full. It's complete because all of the nodes, because it's full from A down to D, E, F, G, this is full. And then the last level, all of the nodes are as far to the left as they can be. So that means it's complete. It's not perfect because there are nodes that don't have children. There are nodes that are not leaves that don't have. There are. This is a perfect tree because all of the leaves are at one level, and all of the internal nodes have two children. Anyway, you can think about that for a while and sort of try to commit that to memory, although it's not super important. All right, so let's do a challenge. Okay, this is we're just supposed to say what all of these the answers to all these questions. So let's start it up here. I'm going to do 2. Okay, you can do 1 and 3. What is the depth of C? C is right here, so the depth is how many edges up to the root? 1, 2, 3. So the depth of C is 3. What nodes are in level 3? This is level 0, this is level 1, this is level 2, this is level 3. I think it's just C. If I got my level, if I'm counting my levels correctly, let's see. Let's see, it's counting levels. Where's levels? All nodes. Oh, level 0, level 1, level 2. Yes, okay. Level 0, level 1, level 2. Level 0, level 1, level 2, level 3. Okay, level 3 is C. Great. What is the tree's height? It's the depth of the most distant node from the root, so it's be 3, I guess. A tree's height is 2 because there's 2 edges. So there's 3 edges here, 1, 2, 3. So tree's height is 3. All right, very good. Okay, you can do 1 and 3. Application of trees. Okay, this is kind of an interesting section here. I don't think there's any challenges or anything, but it talks about different applications of trees, and you can think of your own. We've got this is, for example, the file system hierarchy, which can be represented by a tree. These are files. These are directories, and directories have other directories and files. So on. The leaves are the files, and the directories are the internal nodes you can think of. Here's another application, and this is completely new to me. I've gone through this. You can go through this here and try to understand what they're talking about, how to partition up cataloging objects into regions, for graphics and graphics applications, and deciding which objects need to be rendered and which do not. This is another application of trees, so you can go through that, try to understand that. Binary search trees. This is now we're getting into the nitty-gritty of binary trees. This is a real useful and important use for them. A binary search tree is a form of an especially useful form of a binary tree is a binary search tree, which we'll abbreviate BST, and it has an ordering property that any left node subtree keys are less than or equal to the node's key. And that property enables fast searching for an item. And so the idea here is that anything on the left is less than, and anything on the right is greater than, and that goes for all the entire subtree. So if we have D here, the entire left subtree, all the keys are going to be less than D or equal to. And for the right subtree, all the keys, all the nodes in the right subtree are going to be greater than or equal to D here. And so here, for example, this is a binary search tree because at every node, the left subtree is less than or equal to, and the right subtree is greater than or equal to. And this is not a binary search tree because the left subtree is greater than the key is greater than 5. 7 is greater than 5. This is not a binary search tree because 7 is greater than 6 and 7 is to the left. 7 is a member of the left subtree of 6 and 7 is greater than 6. So that's not a binary search tree. This is a binary search tree because at every node, the node on the left, all the nodes on the left, at every node, all the nodes on the left are less than or equal to, and all the nodes on the right are greater than or equal to. So that's a valid binary search tree. All right, let's go back to presenting here. So when you're searching through a binary search tree to find a desired key, it's pretty easy. You're sitting at a node. Is the current node equal to the desired key? No, if it is, you found it. If it's not, if it's less than, if the desired node is less than the current key, then you go to the left. If the desired node is to the right of the, if the desired node is greater than the current node, then you go to the right. So if the desired key is greater than the current node, then you visit the right child. If the desired key is less than the node, you go to the left child. And you keep on doing that until you either find it or you run out of nodes. If you run out of nodes, that means it wasn't in the binary search tree at all. Otherwise, you'll find it. And so here's a binary search tree may yield faster searches than a list. Well, of course it does, because in theory, if it's a perfect binary tree, you only have to look at log to the base 2, log to the base 2 searches. It's just like a binary search. Whereas with a linear search, you gotta if it's a linear search, then yes, of course, it may take longer. To do a binary search on something like this, you have to be able to index it. You have to be able to go directly to D without starting at A. And of course, with an array list, it is that way, but with a linked list, it's not. But this thing, a binary search tree, can be linked. The nodes can all be linked up. So you get the advantage of having nodes linked in, which means it's easy to insert them in the middle and so on. That's the advantage of a linked list over an array list, is that you can insert something right in the middle and you don't have to shift anything. Binary search tree, same thing. You don't have to shift anything. But with a binary search tree, you can search for keys for items in log 2 amount of time. This is a chart which sort of lists what these values are for log to the base 2. If there's it's basically the height, the height, because you're either going to go down, you're either going to go down the left or go down the right. So each time you do it a test, each time you do a comparison, you're gonna go down one more level. And so that corresponds to log to the base 2 of this, and so on. So you can see this chart makes sense. For 16 nodes, the height is going to be 4, because log to the base, the log to the base 2 of 16 is 4. And log to the base 2 of n is 4. Okay. So anyway, so searching a perfect binary tree with n nodes requires only O of n log n comparisons. Okay, just like a binary search. Some more terms. Okay, so So when we're traversing through a binary search tree, this in order search you're basically just searching through each node at a time, and if you were to print out the order, the in order traversal of the tree, you get all the nodes in order. So here we have a binary search tree, and when we search in order, we start way to the left. It's a depth first search. No, first we visit the left node, then we visit the node we're at, then we visit the right node, and so it ends up being we visit this one, then this, the B, then C, then D, then F, and then G, and that's the binary search tree ordering. The successor follows in ordering. See, so D is successor to C, and D's successor is F, and so on. All right, so let's do this. Let's do a challenge here, and then maybe we'll finish up this here video sections 1, 2, 3, 1, 2, and 3. All right, let's do. Does node 11 and the node subtrees obey the binary search tree ordering property? Does 50? Okay, so let's try. I'll do 3. Number 3. Okay. In searching for 59, which nodes are visited? In searching for 59, I'm searching for 59. Okay, so I start at 42. I visit 42. Am I supposed to write them here? Okay, first I visit 42. Oh, wait a minute. Am I supposed to put commas? Supposed to put commas and spaces. Okay. First I visit 42. And then I visit 59 is greater than 42. So I go to 53. I visit 53. 53. 59 is greater than 53. So now I visit 70. And 59 is less than 70, so I would go down the left subtree of 70, but there is no left subtree, so I've run out of nodes, so I didn't find it, so the node is not found. Okay, so that's how you do that. This one would be, what is the predecessor of 65? So it would be 54. And what is the successor of 65? Would it be 66? All right, these are pretty easy. All right, so I have taken you through chapter 19, section 1, 2, and 3 on binary search tree. Next time we will talk about, we will actually talk about the search algorithm and inserting and removing. So thanks for watching.